Okay, thanks. This is joint work with Lorenzo Magnolfi, who's in Florence right now, and John McClure, who's right here. And I'm Alan. I need to quickly say we're going to use some Nielsen data in this project, and they want us to say that our conclusions and analyses are ours, not theirs. So the motivation here is that estimating demand systems in differentiated product markets is important in a lot of different settings. Certainly in my field of empirical organization, industrial organizations, it's something we do all the time. And there's a large literature that's developed some nice tools for doing this. And we think of there being sort of two fundamental approaches. One is what's called the product space approach. The other is the characteristic space approach. In the product space approach, you define preferences over the products themselves. In the latter, you define preferences over characteristics of products. And those are the more familiar models like BLP, right? And both of these approaches have strengths and limitations. I would argue that one of the advantages of product space models is that they just are more conceptually clear. And also, the models that you end up estimating are computationally straightforward. The problem is that even the simplest formulations of these product space models have an enormous number of parameters unless you impose a lot of restrictions. On the characteristic side, what's nice is that there are some wonderful theoretical properties of characteristic space models. They can be sort of theoretically founded very nicely. And if you estimate them flexibly enough, they can deliver really rich substitution patterns. The problem, of course, is that if you make them very flexible, they become burdensome computationally to estimate. But for our purposes today, the main problem that I would point out with characteristic space models is that in some contexts, you may have difficulty getting data on the characteristics that matter, either because you don't know exactly which characteristics matter most for demand, or it's just hard to get data on them, even though you know which ones they are. So what we're going to propose to do, this is a very practical thing that we're proposing to do, which is to just bring in auxiliary data, complement the existing demand estimation methods with product embeddings that are computed from these auxiliary data. So the idea is going to be that the embeddings can be used in either type of model. In the product space type model, what we'll do is we'll use pairwise distances from the computed embedding to discipline the cross-price elasticities. And in a characteristic space model like BLP, we can just use the coordinates from the embedding as the characteristics themselves. And the empirical illustration that we'll use for this paper is to estimate demand for breakfast cereal. This is just what people in industrial organization do these days, is estimate demand for breakfast cereal. While some scholars are wasting their time figuring out digital addiction, we're going to solve the harder problem of demand for Fruit Loops. That's what we're up to. So no, but seriously, I mean, the reasons for using breakfast cereal in this context are good ones. One is that it's easy to compare to prior papers' results, but more importantly, there are known characteristics of breakfast cereals that have been used to estimate demand, and we can compare what we get from embeddings to what we would get from using those same characteristics. That's going to be the key thing that's nice about cereals. So what do we mean by a product embedding here? So the idea is that we're going to run an online survey that's just going to ask people, is product A closer to B than it is to C? Okay, and what that delivers, I'll be clearer about this in just a moment, but what that delivers is what's referred to in the machine learning literature as triplets data, just a large number of comparisons that A is closer to B than C is. And so then we can use, there are a variety of algorithms that you can use, but for triplets data, I think the standard is to use this t-distributed stochastic triplet embedding algorithm to compute the embedding. And of course, the embedding, in some audiences, I wouldn't expect people to necessarily know what an embedding is, but here I'm guessing a lot of people already do. An embedding is just going to be a continuous vector representation of, in this case, the products, the cereals, in a low-dimensional latent space. And if you're unfamiliar with the algorithms that do this, it's rather intuitive. You're just choosing coordinates for all the products in some latent space to try to rationalize all these triplet comparisons that you see in the data. You know, position Fruit Loops close to Lucky Charms because in the triplets data, it's often said to be close to Lucky Charms. So the thing that's nice about this is that it should be pretty easy and cheap to do for most consumer products that you might be estimating demand for. So how does this look for breakfast cereals? The survey that we ran looks something like this. You show, in this case, we did this using University of Wisconsin undergraduates and Mechanical Turk workers. You show them a sequence of pages that looks like this. On the left-hand side, there's a reference cereal, in this case, Fruit Loops. And then on the right, there are 8 alternative cereals. And you ask them which 2 cereals on the right are closest to this reference cereal on the left. And you could do this in a lot of different ways, but what's useful about this particular setup is that for this number of reference products, we get 12 triplets from every page, right? Because the 2 products that you say are closest are closer than the remaining 6, so that's 12 triplets from every page. So when we did this with undergraduates, we had them fill out a sequence of 20 pages, which takes them about 5 minutes, and in 5 minutes, they've delivered 240 triplets. So very quickly and very cheaply, it's really cheap with undergrads because it costs extra credit points, right? And overnight, you can have tens of thousands of triplets. If you do it with Mechanical Turk workers, it's still quick. It costs maybe $300 to get tens of thousands of triplets, okay? And that's ample data to train one of these embeddings. So that's what I mean when I say it's sort of cheap and easy to do. So you can compute the embedding in many dimensions, of course. If you compute it in 2 dimensions, what's nice is that you can plot it. That's what I'm doing here. It's too small to see, but here, I've got some zoomed in slides. So this is what it looks like after we sort of run this survey, collect the triplets, and compute the embedding. It sort of delivers a cloud in 2 dimensions. And this is the northeast of that cloud. You can see that it's sort of appropriately clustering together a whole bunch of sugary, fruity cereals. And in the sort of southeast corner, it's clustering together a bunch of chocolatey, sugary cereals. So just eyeballing, that's another thing that's nice about breakfast cereals is that it's a familiar enough product category that we could just sort of eyeball this and see that we're getting something reasonable with the embeddings. So how then are we going to use these? It's important here that the survey is not at all intended to recover preferences themselves. We're going to estimate preferences using the usual price and quantity data. The idea is that the embedding is going to complement the usual price and quantity data. I mentioned in the product space models, we're going to make the cross-price elasticities functions of pairwise distances. And in the characteristic space models, we can just use the embedding coordinates as the characteristics. Okay, so our empirical exercise is going to be to estimate both types of model using data from Nielsen on breakfast cereal sales. And in each case, what we want to do is compare what we get from estimating demand using the embedding to what we would get if we just use observed characteristics. And the observed characteristics we'll use are the same ones that other people have used in this context, which is sugar, fiber, calories from fat, and then sort of a category indicator for whether it's a kid's cereal or an adult cereal or a cereal that anybody could eat. Okay, so in the product space, there are different kinds of models that we could estimate in product space. We're going to do something super simple, which is just estimate a log linear model, where the log sales of a given product is a function of its own price and all of the rival cereals' prices. But what we're going to do is we're going to make the coefficients on the rival prices be functions of pairwise distances. So the cross elasticities are just going to be functions of product distance from the embedding, in the case that we're using the embedding, or in the case that we're using just observed characteristic data, it's going to be distances, Euclidean distances calculated from those sugar, fiber, and calories from fat and so forth. Okay? Now, it's important for the distance function, for reasons I won't go into right now, it's going to be important for the distance function to be estimated flexibly. We experimented with various things, sieves, B-splines, and so forth, and what we found is that a simple cubic polynomial did really well, and so that's what we're going to show you for today. And then we scale the distances by the maximum observed distance in the embedding. I want to just quickly note that we're using this really, really simple log linear model because it's just convenient for showcasing the usefulness of the embedding. If you want to do something that's more theoretically grounded, you could, of course, estimate something like the Deaton and Muehlbauer almost ideal demand system, the AIDS model, and we've done that, and that's in an appendix of the paper. But this is just really easy to interpret because, of course, the coefficients themselves can be interpreted directly as elasticities, which is what we want. So here's some results from this log linear demand model. On the left-hand side, this is just the comparison of the distribution of estimated own price elasticities. One of those lines is for the embedding version, and one of those lines is for the version that just uses observed characteristics, and the point, of course, is that the lines are close. It's not surprising that the own price elasticities are similar because those depend more on just the price quantity data, the own variation in the own price of the cereal, not on what's happening with rival prices. But you'll see that the distance function that we estimate, the line that's, I believe, blue is from the embeddings model, and that has the shape that you would expect. The magnitude of the cross-price elasticity is larger for products that are nearby in the embedding. If we calculate distances from observed characteristics like sugar, calories from fat, and fiber, which is what other analyses would have done using observed characteristics, we get sort of a funky and implausible looking distance function because it's non-monotonic. Overall it's kind of flat, so it's not that helpful. What I think is maybe more useful is to look at some examples of the estimated cross-price elasticities. What we've got here is sort of two pairs of similar products. Honey Nut Cheerios is very similar to Honey Graham O's, and Cocoa Pebbles is very similar to Cocoa Krispies. And what you see, first of all, let me just point out that the own price elasticities, they all end up being reasonable, and they're, I should have explained this. In each cell of this table, the top number is from the embedding version, and the bottom number is from the version that just uses observed characteristics. Okay? So what you see is that the own price elasticities are basically the same. We already talked about that. What's more interesting is the cross-price elasticities, and here what I've highlighted are cross-price elasticities between similar products. And what you'll notice is that, for instance, the cross-price elasticity between Honey Nut Cheerios and Honey Graham O's is larger in the embedding model than it is in the one that uses observed characteristics, which is good news. And similarly for Cocoa Pebbles and Cocoa Krispies, we get larger cross-price elasticities from the embedding version. And then if we look at dissimilar products, like in this case Honey Nut Cheerios and Cocoa Pebbles, the embedding version gives a smaller cross-price elasticity than the one that's based on observed characteristics. So those are sort of encouraging results. It looks like what we would argue is that we're getting more plausible looking substitution patterns if we use the embedding than if we just rely on observed characteristics. So we do a similar exercise for BLP, and as some of you may know, estimating BLP is a giant pain in the ass, and I've got some details here about exactly how we implement it. We mostly try to mimic the implementation of a recent paper by Matt Backus, Chris Conlon, and Mike Sinkinson. We've got product and weak fixed effects. We've got random coefficients on some of the variables and interactions with demographics. And we're using the differentiation IVs that are recommended by Gandhi and Hood. And we're using the PyBLP software to estimate this. What matters, of course, in the end is what are we getting out as estimates of elasticities, depending on whether we're using the embedding as product characteristics. So we just sort of plug in coordinates from the embedding. I mean, the problem with that, of course, is that there's no interpretation of these latent characteristics from the embedding, unlike sugar, which you know exactly what that measures. But of course, the problem with sugar, calories from fat, and fiber is that they might not be measuring exactly what consumers care about, right? So same table structure here, where in each cell, what we've got are elasticities on top from the embedding model and on the bottom from observed characteristics. And again, the own price elasticities are reasonable and very similar to each other between the two models, but the cross price elasticities differ somewhat. If you look at similar products, again, we're getting larger cross price elasticities when we use the embedding. and we're getting smaller cross-price elasticities when we, for the embedding model when we look at dissimilar pairs of products. So again, honestly, for BLP, we were sort of going to be happy if we could just get the embedding to deliver similar looking elasticities to what we get from incorporating observed characteristics. And it turns out that I think for BLP, we're willing to argue that in fact the elasticities look more plausible from the embedding model than from the observed characteristics model. So, lessons from this exercise. One, the method's really easy to implement. This is a really easy thing to do because the survey is quick and cheap to run, and the embeddings are totally straightforward to compute using existing algorithms. And also, the results appear to validate the method in the sense that when we look at the results we're getting from using the embedding, if anything, look better than what we get from using the kinds of characteristics we would use if we were just using observed data, right? And an important implication of this, and what was largely motivating this exercise to begin with, is that this is telling us that in circumstances where we don't have good data on product characteristics, then using these auxiliary data to compute an embedding and then treating those as characteristics is going to work, right? Now, it could be that this doesn't generalize beyond serial, but at least that's what we hope this exercise is illustrating, is that there's some hope in markets, which we think are fairly common, where you want to estimate demand, but you don't have good data on product characteristics. And our next application, which we think is going to be much more interesting and more important than breakfast cereal, demand for Fruit Loops, is to competition in the market for mobile apps. So what you want to know, or one of the important policy questions in antitrust these days is, should we be preventing Google from acquiring Waze, or should we be preventing Facebook from acquiring Instagram? And in ordinary product markets, we have existing methodologies that help us answer that question. We estimate demand and we get cross-price elasticities, and we say, hey, they're acquiring a very close substitute, and usually we don't want that to happen. The problem is, it's hard to estimate demand for mobile apps because there are no prices, right? So that's already a problem. But then more relevant to what we're doing here is that it's really hard to say what exactly are the relevant demand characteristics, or sorry, product characteristics that are relevant to demand that would allow you to implement the existing methodologies for demand estimation. So what we've done is we've run a survey and computed an embedding that positions apps in a latent space. We have some data on app usage, and what we're going to do is combine the embedding data with usage data to estimate a demand model for mobile apps where sort of the currency in that model is time, not price, because most apps are free. So it's sort of a time usage model that will deliver, we hope, good estimates of which apps are close substitutes for one another that'll be relevant to the sorts of antitrust questions that are being asked. Okay, I'll stop there and see if there are questions. Yeah, you mean for the mobile apps thing? So the question is, how do we define the market for the mobile apps? I mean, the market potentially is all apps, right? Yeah. But what we've done is we've taken about 90 of the highest usage apps, and that's going to be our market.
So within, for example, iOS store or Store?
Mm-hmm.
Okay.
Yeah. Go ahead.
This might be a very basic question for this application, but is there any way to measure out of sample performance? Is there any way to validate these sort of intuitively they look better, but is there any way you could hold out some data and then show that it better predicts what?
Yeah, so this is a really good question. Let me repeat it. So the question is there any way to validate this using an out of sample test? We've thought about that. We've tried a couple things. The hard thing is so some things you could do is sort of after what we thought about doing, for instance, is after the introduction of a new product, there's this chocolatey cereal that I had never heard of called Crave that was introduced during our sample period. So one thing we thought about doing is predicting the market share responses of other cereals to the introduction of Crave. So that kind of thing we're going to try to do. That one didn't work very well, but I think it's partly just because it's really, really hard to predict what's going to happen in these cases. So just like all predictions suck. Go ahead.
One other question. So in this case, thinking about antitrust, how much would this kind of approach be applicable if I believe that there was not just substitutability, but like the opposite, like super additivity, right? So like, yeah, so like one of the things that's like really gross about like companies that steal all of our data or take all of our data is that they often work together better than they work by themselves.
Yeah.
And I'm wondering, I guess distance probably doesn't capture that, is that right?
That's a really good question that I haven't really thought about, because most of the markets that I'm thinking about are ones in which we're not worried about complementarities. I mean, certainly in principle, you could estimate negative cross-price elasticities, right? That's a complementarity on the demand side. But I think what you're alluding to is not necessarily a complementarity on the demand side, but maybe on the supply side, because they're using the same data and it's valuable to them to have data from different products.
I could imagine it both ways.
Both ways.
Yeah.
Yeah, so I mean, at least.
I use Instagram and that makes Facebook more valuable.
I see. So certainly, like in the log linear model, you could estimate negative cross-price elasticities for sure. So that could work. Yeah.
Just a quick question. So if your survey takers decide which product is closer to which, in part based on prices, based on how close the prices are,
Yeah.
is that going to cause an issue in estimating the price elasticity?
Would you repeat the question?
Yeah, I will. So the question was, if the people who are responding to the survey, when they're thinking about which products are close to each other, have prices in mind, and they're saying product A is close to product B because the prices are similar, is that problematic for estimating price elasticities? That's a really good question. My instinct is probably. But I don't have a good answer for that question. But
Which direction?
yeah. No, that's a good question. I mean, that's one of the hardest parts about what we're doing here is like, we just have no idea what these people are thinking when they answer the questions, which is unfamiliar territory for economics, right? We like to have a model of what everybody's thinking when they do stuff, but here we don't. So yeah, we're kind of stuck.
Great.
Thank you.
The speaker again, and thank all of the speakers.